Hi, I'm Scott Moore, and today I'm going to tell you about a new shell scripting language I've been developing with Christos, Dimoulas, Dan King, and Stephen Chong. But first, why do we need a new shell scripting language? Well, we use scripts to do all sorts of things on modern systems, like actually orchestrate the startup of our system, automating system administrative tasks, and just generally getting stuff done. But how do we know that all of these scripts we're writing are actually doing what they're supposed to do, and in particular not doing anything else? So most people probably just ignore this question, but some people, maybe like the person who posted this to Stack Overflow, would like to actually try and figure it out. But ultimately in vain, because understanding the effects of running a script doesn't just require scrutinizing that script's code in great detail, but also understanding the entire environment in which it's run. And this goes against some kind of fundamental security principles. So 40 years ago, Salter and Schroeder told us about the principle of least privilege, which says that every program should operate using the least amount of privilege that's necessary for it to do its job. So for example, so if we can give a script just the authority it needs to do our job, we can protect ourselves in the case that it's malicious or it has bugs. So if you think about this recent shell shock vulnerability, this was made much worse by the fact that every bash script on your program could launch new shells or create new network connections and actually do some serious damage. Unfortunately, applying this principle to shell scripts raises a few key questions. So first, how do we actually go about limiting the authority of scripts? And second, once we've done that, how can we actually figure out what authority is necessary in the first place so that we can give it to the script? So SHILL is a scripting language that we've designed to answer these questions and support the principle of least privilege on commodity operating systems. So in SHILL, every script that you write or download off the internet comes with a declarative security policy that's enforced by the language runtime. And of course, SHILL scripts can call other scripts and even arbitrary executables. So in that case, to ensure that the security policy isn't violated, SHILL uses a kernel module to sandbox the execution of that executable. And in this way, SHILL provides end-to-end enforcement of a declarative security policy. And these policies can serve both as a declarative way to limit the authority that you give to scripts, and as an interface that tells you what authority a script needs to execute so you can decide whether or not you think it's safe. So to do this, SHILL relies on three key features: capabilities, contracts, and capability-based sandboxing. So capabilities make the authority that a script has explicit, rather than a property of the environment in which it's running. Contracts let users control how scripts can use the capabilities that they're given and provide those declarative interfaces that describe what authority a script needs to run. And then SHILL uses capability-based sandboxes as a mechanism to extend the guarantees that we get from capabilities and contracts onto the arbitrary programs that a script might invoke. So in the rest of this talk, I'm going to describe each of these features in turn and then tell you how they come together to achieve SHILL's security goals. So first up, capabilities. As you're probably familiar with, a capability is an unforgeable token of authority. So you can think of this as something like a car key, where just possessing it gives you the ability to say, open the car door and actually drive off with the car. And you can contrast this with discretionary access control in Unix, where doing something like opening a file relies on properties of your environment. So which user is currently executing the process and how the permissions on the file are set up. Capabilities have a long history as a security mechanism, starting with capability-based operating systems, and more recently developed in programming languages and tools for doing things like application compartmentalization, like the Capsicum tool for FreeBSD. But to get an idea of how capabilities are used in SHILL, I want to show you an example SHILL script. So this script copies files from one directory to another. And hopefully, it looks a lot like something you might write in a language like Python, right? It just loops over the contents of a directory, creating new files and copying the contents over. The thing to note here is that instead of manipulating paths, this script manipulates capabilities. So in SHILL, there are capabilities for things like files and directories, but also for stuff like pipes and sockets. And the key thing is that any dangerous operation using system resources, you have to have a capability to do. So each of these different types of capabilities comes with a set of operations, which each require a different set of privileges on the capability. So for example, listing the entries in a directory requires that you have the contents privilege for that directory. On top of that, some operations can derive new capabilities. So for example, looking up a file in a directory is going to return you a capability for the resulting file. And by default, that derived capability is going to have the same privileges that the parent did. Now, there's two important properties about how SHILL uses capabilities that together we call capability safety. So the first is that all rights to resources on the system are represented by capabilities. So all dangerous operations in the system are mediated by those capabilities. And second, scripts don't come with any capabilities by default. And what this means is that you can reason about the effects of a script just by considering what capabilities you pass in as arguments. So for example, when I'm calling this script, I can know that the only effect it has on my system is to modify files and directories that are inside of those directories I passed in as arguments. So SHILL's second key feature, contracts, builds on the security that we get from capabilities. So software contracts were introduced by Bertrand Meyer in the Eiffel programming language, and these days you can find them in lots of other places. And the idea is that code should come with executable specifications of the pre- and post-conditions for it that can be verified at runtime to ensure that all of the components in your program are interacting as they're supposed to. So this is a SHILL script that returns the list of all files with the extension .c in a directory. And the top here is a contract for the function, which acts as an executable specification for it. So for example, this contract says that the argument that the caller provides must be a directory capability, and that the function will return a list of file names. And these contracts are actually written in SHILL itself, so users can extend the specification language to meet their own needs. And what SHILL will do is keep track of this contract at runtime and halt the script if the contract is violated. And so in this way, contracts are a useful tool for composing scripts together because they let different components rely on the fact that their interface is satisfied. But where SHILL differs from other languages that have software contracts is that we don't use them just to catch this type of bug. We also use them to enforce security. So here, I've replaced the contract for this function with a more precise contract specifying that the argument must be a directory with the contents privilege that lets the function list the entries in the directory. And crucially, this type of capability contract both requires and restricts the privileges that are given to the function. So the person who wrote the function can rely on being given sufficient authority to complete their job, and also provide a specification to callers that they can use to decide whether or not they think this function is safe to invoke. But because this contract also restricts privileges, the caller is guaranteed that this function will only list the contents of the directory, and it can't, for example, create any new files or read from the files that were already there. So the third key feature of SHILL is capability-based sandboxing. So you've probably been thinking that one of the key characteristics of scripts that doesn't seem like it's appeared so far is that they often call other scripts or programs to actually get their work done. So suppose I'm writing a script to test some software that I just wrote. At some point, I actually need to run the program that I just compiled. But this program could do absolutely anything, right? So to be able to use SHILL for this type of task, I need a way to enforce its security properties on arbitrary executables. And the way we do this in SHILL is by emulating capabilities in contracts using a mandatory access control policy. And just before I show you how that works, I want to show you what executing a program in SHILL looks like. So you have this execute statement, which takes as arguments a file capability for the program that you want to run, a list of arguments, and a set of capabilities for things like standard in and out and error that you're going to need, and also a collection of additional capabilities that you think this program may need to do its job. SHILL is then going to create a sandbox using a mandatory access control policy. And I'm going to show you how this works using an example. So suppose I want to execute this simple program when I'm currently in the directory Bob of this file system. The first thing that the MAC policy is going to do is label the kernel objects that the sandbox has capabilities for with the privileges that were associated with them. So here I have capabilities for the Alice directory and the Bob directory. Then we'll start executing the program. And when we get to a system call, the MAC policy is going to interpose on all of the low-level kernel operations that it causes on individual objects within the kernel, and check them against the privileges that we told the sandbox we should have for those. So here, I'm going to start by checking that I have lookup privileges for the directory Bob. I do, so this first operation will succeed. Next, I need to look up Alice in the home directory. But you'll notice here I don't actually have any privileges for home, so we'll prevent the action, and the system call is going to return with an error. Of course, this isn't a super interesting example, so I want to consider the case where I actually had some capability for this directory. In this case, the lookup will actually succeed. And finally, I'm in the state where I need to look up the file dog.jpg in the directory Alice. So again, I have the necessary privileges, and the lookup is going to succeed. You'll notice here, though, that there's this extra annotation on the lookup privilege that says with read. What this annotation says is that any capability that I derive from the Alice directory should have the privileges read. So what the sandbox is going to do is propagate this information to a derived capability on dog.jpg. Finally, the system call is going to succeed, and the program can continue executing. And basically, what this capability-based sandbox is doing is emulating the behavior of an application that is aware of capabilities. And this gives us a flexible mechanism that lets us execute legacy code while still enforcing the security guarantees of a SHILL script. I should briefly mention that it turns out on Unix, it requires lots of capabilities to run an executable. So for example, just calling cat on a file requires all of these different capabilities. In SHILL, the way we handle this is through an abstraction we call a capability wallet. A capability wallet gathers together related capabilities with contracts, and SHILL standard libraries use them to package up necessary capabilities for running executables and provide what looks like a familiar path-based interface for running them, but is mediated by capabilities. I invite you to actually look in the paper to see more about what these are and how we use them for security. Okay, so now that I've described SHILL's key features, I want to show you how they go together in SHILL's architecture. So suppose I download some capability-safe script that I want to run on this file foo.txt. So the first thing I can do is look at the contract on this script to give me some guarantees about what it will do. So in this case, among other things, it tells me that I'm just going to read from the file that I give it a capability for. Now, there's one step I haven't told you about yet, and that's where did the capability that I'm going to give this script actually come from? And this is a common problem in most capability systems, the need to actually bootstrap some initial set of capabilities. The way we solve this in SHILL is through a special type of script called an ambient script. And an ambient script provides glue between the world of discretionary access control and the world of capabilities. And the important thing about it is it has very limited expressive capabilities. Basically, all that it can do is create a new capability for some system resources, like foo.txt, and then pass them into a capability-safe script. Okay, so now that we have a capability, we're going to wrap it with information about its contract so that we can enforce at runtime that only the read operation will be called on it. Of course, at some point, this script might want to run some executable. When that happens, SHILL will create a sandbox to execute it in. Then if we pass this sandbox a capability for foo.txt, SHILL's going to record the privilege information that was associated with the contract on the underlying file system object. Then when the executable is actually running and it tries to access this resource, its access is going to be restricted by the privileges that I put on that. So now you have a big picture of how SHILL works. I want to tell you about one of our case studies to get a picture of how it works in practice. So last semester, I was a teaching assistant for a programming languages course, and one of my jobs was to grade all of the submissions. And it turns out this gets really tedious after a while. So you have to create all these files and copy things around and compile code and run tests and record grades. It gets old really fast, so I wanted to automate it. So naturally, I wrote a script. And this does a great job of simplifying my life, but it doesn't actually address all of my security concerns I have. So for example, I'd like to make sure that none of the submissions I'm running can clobber all my files or delete my email. Second, I want to make sure that the test suite doesn't get messed up while I'm doing the grading or maybe leaked to the internet for future classes to use. And third, I'd actually like to make sure that grading one student's homework can't interfere with grading another student's homework so that students can't cheat or just otherwise mess with the grading process. The idea with SHILL is that I can reuse all of that code I wrote to automate my task to achieve these security goals. So to demonstrate this, I'm not actually going to show you any of the code for the grading script, but I'm going to show you the contract for a function that grades a single student's code. And this contract serves as a declarative security policy that I can actually use to reason about the security of the script. So you can see it here. As you can see, it takes a number of arguments. There's the actual submission to grade, a directory full of tests, a directory in which I can do the compilation and testing and things, a log to actually write the grades to, and one of those capability wallets I told you about that has capabilities for the libraries I'm going to need. And then I can look at this contract and actually use it to try and address those security concerns I had before. So first, I know that running this script can't corrupt any of my other files or delete my email because I'm not going to pass in capabilities for those. And then second, I can look at the contract on the test argument and see that it's read-only. So I know that it's not going to be modified. And on top of that, I can look at the contract and see that there aren't any capabilities for the network. So it's not possible for this to get leaked to the internet. And finally, I can even reason about whether or not the submissions can interfere with each other. So if I look carefully at this contract, I can see that there's no way for one call to this function to get read privileges to a file or other capability that a different call to the function has write privileges to. And this way I can reason about whether or not these two different invocations for the different students can communicate with each other. And the great thing is that I get all of these security guarantees, even if the implementation of the grading function was wrong and doesn't do what it's supposed to do. So in this way, SHILL makes it possible to express and enforce ideas of least privilege in a way that's composable and actually easy to reason about. So I'd like to take a little bit of time to tell you about our implementation and how we evaluated SHILL. So our prototype of SHILL is implemented as a capability-safe subset of the Racket programming language, along with a new capability-based systems library for it. And to implement that library, we actually needed to add a few additional file descriptor-based system calls to FreeBSD. The Capability-Based Sandbox is implemented as a policy module for the FreeBSD Trusted Mac framework. So we evaluated SHILL through a number of case studies. The first one I already told you about was a set of grading scripts for a programming languages course. The second one is we used SHILL to develop a set of installation and uninstallation scripts for Emacs. So these scripts sandbox the various stages of downloading and compiling and installing Emacs, and also give you a fine-grained policy that tells you what files will be installed and what files will actually be removed by the uninstaller. Third, we used SHILL to develop a sandbox for the Apache web server that restricts it to read-only access to its configuration and content directories, and also prevents it from creating any new outgoing connections. And finally, we implemented a find and execute style task where we used find to identify every C file in the BSD source tree and then run grep on each of them in its own capability-based sandbox. So I'll just quickly present some performance results. You can find a much more detailed evaluation in the paper. So at the bottom of this slide, you can see the performance of each of our 4 case studies when run without SHILL, using SHILL just to programmatically create a sandbox, and implementing more of the task in SHILL to get fine-grained security guarantees. And there's 2 main takeaways I want to point out. So first, the overhead for our case studies is pretty reasonable, generally lower than 20%. There's one outlier you probably noticed, which is this find and execute task, which is about 6x overhead. It turns out it spawns thousands of sandboxes in a really short period and was putting a lot of stress on how our prototype dealt with cleaning up old sandboxes. It's not a problem that's fundamental to our approach, and we're actually currently working on a fix. So the second takeaway is that the overhead of SHILL is proportional to the security guarantees that you get. So if you just have SHILL installed, but you're not actively using it, there's a negligible overhead. And then if you use SHILL to just programmatically create a sandbox, you'll pay some small amount of overhead. And that increases as you write more and more in SHILL to get stronger and stronger security guarantees. So to sum up, SHILL combines a number of different ideas from both system security and programming languages design in order to support the principle of least privilege on commodity operating systems. We're actually super excited about this project, and I'd like to invite you to go to our website, shillang.org, where you can actually download the code or a virtual machine with it pre-installed and try SHILL out for yourself. So thank you very much, and I'm happy to take any questions.
Yeah, so this is Xu Zhao from University of Toronto. I still have questions about your motivating example. I mean, even using SHILL, the user can still download a big script and ask that the capabilities or contracts in this script there are so many items that cannot verify them one by one. So what should I do?
Yeah, so I mean, ultimately, the user still has the task of deciding whether they think it's safe to run some script or not. The key advantage is that unlike downloading a bash script or something, where you, as I said, you have to look at both the code of the script and understand how you've configured your system. Now you can just look at the specification at the top of the script, and while it may be complicated, it's just one place to focus your attention.
Okay, thank you.
Injur from Columbia University. I have two questions. So first, you use capabilities to do access control. So traditionally, there are two types of approach. One is access control list, another is capability. So what drives you to use the capability instead of the access control list? And the second question is, how do you compare USENIX? Thank you.
So the first question was why capabilities instead of access control? And the reason is fundamentally is we wanted to turn the decision of whether or not a script is secure to run into kind of a local question that you can look at kind of at the interface, rather than a configuration question about the environment. And with regards to SELinux, in some ways the systems are fairly similar in that they're using mandatory access control. The key difference is that SELinux kind of relies on creating a system-wide policy, whereas with SHILL, you can actually kind of on a per task basis describe the policy that you want for your application.
Hi, Brian Ford at Yale. Very nice work, very nice practical use of capabilities. I like it a lot. One question, it seems like one downside of your capability wallets and sandboxing model is that it seems like you still risk confused deputy problems, which is one of the things that kind of the capability model was hoping to address. For example, a program that you call, you have to give it 2 directories, and like for your grading script, and oops, it got tricked into using the grade script, the test suite capability to read a file that was actually supposed to come from the student's, source directory. Do you have any? Have you thought about how you might address those kinds of risks?
So I don't have any concrete ideas about how to address it in the context of a sandbox. I will say you are right that our sandboxing mechanism is vulnerable to this kind of attack. This is actually one of the reasons that we chose to implement a language rather than just like a policy language for sandboxes. Because if you care enough about some particular confused deputy attack, you can actually try and port some of the functionality that you're worried about into SHILL, where actually by reasoning about the language itself and your script directly, you can kind of suss that out and make sure that there isn't that attack.
Mm-hmm. Thanks.
Hi, this is Stefan Bucher from EPFL. I was wondering what is the overhead in terms of development time when using SHILL, for instance, because many people resort to shell languages for quickly hacking up something and trying out things. What would be the added cost of thinking in terms of capabilities and contracts?
So I'll say there's kind of an initial cost in that you definitely have to make the switch from this kind of path-based, very quick hack it together to a world where you're kind of manipulating data types and stuff. I might say it's kind of like the difference between writing in Bash versus Python. And then point out that one of the things we like about using contracts as a mechanism for these policies is you can actually start with something that's fairly weak but very easy to write. Like you know it should be a directory and it should be a file that I take in. And then kind of increase the security specification that you put on top of that kind of as you care enough to develop that security policy.
Okay, thank you.
Hi, I'm Ken from UC San Diego. So I have 2 questions. The first one is like, have you ever... One. Actually, I have a quick question, plus a long question. Okay, anyway. So, have you ever tried like using SHILL to apply on like existing scripts to see like whether how many scripts are trying to access something they shouldn't access?
So that's an interesting question. The closest we come to that is some of our case studies were actually things that we had like a Bash version of. So for instance, the grading script example, I actually started with a Bash script that I wrote and kind of translated it into SHILL in a fairly obvious way. And the things that you notice that there's places where, so I mentioned that isolation guarantee that we want. And that requires not just changing the specification, but also slightly restructuring your code so that it works in a way where I can actually give different capabilities to different things. So kind of by default, if you take any script that probably hasn't thought much about security, I imagine you'll have to do a little bit of work to change it for SHILL. Of course, you could always just put it in a big sandbox, and and then you'll get at least some of the isolation guarantees, but as Brian mentioned, you may have to worry about things like confused deputy, and you won't get as strong guarantees.
Hi, this is Ning from CEO Boulder. I'm just wondering if I'm going to run a command using SSH in the local machines, does it also support the security in the remote machines, you know? If I run certain commands uses SSH in the local machines and run the scripts in the remote machines, does it also support that?
So we're not going to give you any guarantees about what happens on the remote machine, but we will give you control over whether or not you're able to, say, make an SSH connection. So you can at least reason about if that's a risk that you're willing to take.